Welcome back to our series of videos on Chapter 4 from our Zane State Physics class. And we are looking at an example where we have a box on a surface. It is not a frictionless surface. There is friction, and we are pulling at a slightly upward angle, a 30-degree angle with respect to horizontal. And we want to know how this box is going to accelerate. And what we have done so far is we have found the normal force. So the normal force is the force that the surface pushes back against the box. And it's not just equal to the weight in this case, because that's not the only force in the vertical direction. We are also slightly lifting the box up with this pulling force. So that reduces the normal force. So the normal force is equal to the weight minus the vertical component of our pulling force. And so in this case, we calculated our normal force is 78 newtons. So now that we know the normal force, we'll be able to find the friction force. And once we know the friction force, we'll be able to determine how this box is accelerating. So let's go ahead now and apply the same second law of motion to the horizontal direction. So that states that the sum of forces equals mass times acceleration. So what are the forces? Let's sum up all of our vertical forces. Well, we have a friction force, and the friction force always opposes motion. So if we're trying to pull this box to the right, friction is going to fight us and pull it to the left. So that's going to the left, so it's negative. So we've got negative friction force. And the other thing in the horizontal direction is the horizontal component of our pulling force. So that would be plus the pulling force multiplied by cosine of 30. So we use cosine to find the horizontal component. And that is going to equal the mass. The mass of our box is 10.0 kilograms multiplied by its acceleration. It is going to accelerate to the right, but we don't know at what rate. We need to calculate that. So let's look at the friction force. Friction force is equal to the normal force multiplied by the coefficient of friction, the kinetic coefficient of friction, plus Fp cosine of 30 equals 10.0a. Just drop the units out. Okay, so the normal force. We just calculated the normal force, and it was 78. So we've got 78.0. The coefficient of friction, I believe, was given in the problem statement. It is 0.30. Plus the pulling force was 40 cosine of 30 equals 10.0a. So we can take our 78.0 times 0.30 plus 40.0 times cosine of 30 and divide all of that side of the equation by 10, and that will give us our acceleration. So we plug that into the calculator, and we should get an acceleration of... Okay, I plugged that into my calculator, and I wasn't getting the right answer, and so it made me realize I made a mistake here. And I could have edited that mistake out of the video, but I like to leave them in because it illustrates some common mistakes that you yourself might make. And that is, I forgot all about this negative sign here. That dropped out of my equation here accidentally, and it should not have. So I need to remember the direction that these forces are going. Friction force is going to the left. So that's a negative 78 times 0.3. That's friction force is going to the left. The pulling force is going to the right, and that will equal mass times acceleration. So I need to make sure I include the negative sign there, and now let's try calculating that again. Okay, that's much better. I'm coming up with the correct answer now of 1.1 meters per second squared. And our significant figures are 2. That's limited by the fact that the coefficient of friction given to us was 0.30. So that is how it is going to accelerate, 1.1 meters per second squared. So again, be careful of when solving these problems. Little things like negative signs, exponents, they have a tendency of, if you're not careful and if you don't write these things out, of just kind of disappearing like it did here. So I left that mistake in the video, so hopefully you can benefit from it. So as I was saying earlier, it's easier to keep something going than it is to start it when it comes to pushing or pulling an object that is experiencing friction. So this graph right here, what this is illustrating is that we can apply a force, and this is how the friction force responds. So initially in this area, the object is not moving, it's remaining static. And so the harder we push, the harder friction force pushes back. It's almost as if friction is like an on-demand force. The more we push against it, the greater it gets, until we finally overcome it, until we exceed the maximum static friction force, and then the object starts to move. And once it does, that friction force drops down and then levels off to the kinetic friction force, which is equal to the normal force times the kinetic coefficient of friction. So in this example here, you can see that the force required to get the object moving was just shy of 40, maybe that's like 39, let's say. And in order to keep it going, looks like that's, I don't know, maybe a little bit less than 30, maybe it's like 29 newtons. So it does require less force to keep an object moving that's already in motion than it does to start it off when you are experiencing static friction. Okay, so the next type of problem we are going to look at is when you have an object that's on an inclined plane. I can tell you from years of teaching statics and physics that textbook authors love these types of problems. They appear in all sorts of textbooks all the time. So what we have here is an object. We'll just say it's a box to keep it simple. And gravity is going to pull straight down, regardless of the slope of the ramp. Whether it's on a steep ramp or a shallow ramp, it doesn't matter. Gravity always pulls things straight down. Now, the normal force is affected by the incline of the ramp because the normal force is always perpendicular to the surface. It makes a 90-degree angle. And then the friction force is going to be parallel to the incline of the ramp. Okay, so it creates some angles. It's going to involve some trigonometry to break some of these vectors down into vertical and horizontal components. If we look at this example problem here, we have a skier. Actually, if you look here at the autograph, I believe this is Lindsey Vonn, and it's written out to Doug. Doug is the author of the physics textbook. So the skier is going downhill, and the slope makes a 30-degree angle. And the coefficient of kinetic friction between the skis and the snow is pretty small, but it is present, and the coefficient is 0.10. We want to know what is the skier's acceleration. So, like all problems involving a system of forces, we want to draw a free body diagram. So we'll just represent the skier with a single point, and we have the force of gravity, mg, going straight down. The force of friction is going to be in the opposite direction as the motion of the skier, and the normal force is perpendicular to the slope. So what I like to do with these problems is to rotate the diagram so that the inclined slope is actually horizontal. I think for whatever reason this helps me to visualize it better. So I've just rotated the whole thing in a counterclockwise direction, some angle equal to the inclination of the ramp. So by doing this, our friction force is perfectly horizontal, the normal force is perfectly vertical, and it's just now the gravity force that's at an angle. Okay, and what it was going straight down, but since I rotated the whole diagram theta degrees, it's now making an angle with respect to the vertical of theta. Now, I've said all along that I prefer to use the complementary angle, the angle that is made with the horizontal axis, for my calculations when finding vertical and horizontal components. So this angle would be 90 degrees minus theta. So in this particular problem, theta was 30 degrees. So the weight of the skier, which was going straight down, is now rotated 30 degrees. And that makes this angle 90 minus 30, or 60 degrees. So now I can use the 60-degree angle to go about finding the vertical and horizontal components of the weight of the skier. So if we sum the forces in the x direction, if we use the second law of motion, sum of forces equals mass times acceleration. What are the forces in the x direction? Well, we have the x component of the weight of the skier. So that is going to be mg cosine of 60. We are also going to have the friction force going in the opposite direction, minus the force of friction. And that's it. Those are the two forces that are present. That is going to equal mass times acceleration. We expect the acceleration to be non-zero, meaning that there will be some acceleration downhill. But we don't yet know what the friction force is, because we don't know yet what the normal force is. We can elaborate here and say mg cosine of 60 minus friction force is the normal force multiplied by the coefficient of friction, and that is equal to mass times acceleration. I think, actually, I just looked down at my timer and saw that I'm down to about 30 seconds left. So I think this will be a good stopping point right here, and we'll resume in the next video.